So, radar detection equipment is a crucial component of modern military operations, providing early warning, surveillance, and targeting capabilities. Here are some types of radar detection equipment used by the military and how they work. First up, pulse Doppler radar. This type of radar uses a series of high-frequency pulses to detect and track targets. It works by transmitting pulses of radio energy, which bounce off objects in the surrounding environment. The radar system then measures the time delay between the transmitted and received pulses, allowing it to calculate the range, speed, and direction of the target. Next, phased array radar. This type of radar uses a large array of antennas to steer and shape the radar beam electronically. Phased array radar can track multiple targets simultaneously and has improved accuracy and range compared to traditional radar systems. Airborne Early Warning Radar, or AEW. AEW radar systems are mounted on aircraft and provide early warning of incoming threats, such as enemy aircraft or missiles. These systems use a rotating antenna to scan the horizon and can detect targets at long ranges. Surface-to-air missile, or SAM, radar systems are used to detect and track incoming aircraft and missiles, guiding surface-to-air missiles to their targets. These systems typically use a combination of pulse Doppler and phased array radar technologies. Synthetic aperture radar, or SR, radar systems use the motion of the radar platform, for example, an aircraft or satellite, to generate high-resolution images of the ground or sea surface. SAR radar can penetrate clouds, fog, and other obscurants, making it really useful for surveillance and reconnaissance. Ground-penetrating radar, or GPR radar systems use radar pulses to image the subsurface of the ground, detecting buried objects such as mines, tunnels, or caves. GPR radar can also be used to detect hidden voids or cavities. Over-the-horizon radar systems use the ionosphere to bounce radar signals over the horizon, allowing them to detect targets at very long ranges, up to several thousand kilometers. OTH radar is used for early warning and surveillance. X-band radar systems operate at high frequencies, between 8 and 12 GHz, and are used for short-range, high-resolution surveillance and targeting. X-band radar is often used on naval vessels and for air defense applications. S-band radar systems operate at medium frequencies, between 2 and 4 GHz, and are used for medium-range surveillance and targeting. S-band radar is often used for air traffic control and weather surveillance. L-band radar systems operate at low frequencies, typically between 1 and 2 GHz, and are used for long-range surveillance and targeting. L-band radar is often used for air defense and early warning applications. These radar detection equipment types work on the following principles. Reflection radar signals bounce off objects, returning to the radar system, which then processes the returned signals to detect and track targets. Doppler shift. The frequency of the returned radar signal changes as the target moves, allowing the radar system to calculate the target's speed and direction. Interferometry. The radar system uses multiple antennas to measure the phase difference between the returned signals, allowing it to calculate the target's position and velocity. Signal processing. The radar system uses advanced algorithms and signal processing techniques to extract information from the returned signals, such as target range, speed, direction, and classification. The military uses radar detection equipment for various applications, including air defense, which involves detecting and tracking incoming aircraft and missiles. Surveillance is another key use, monitoring and tracking targets such as enemy troops or vehicles. Reconnaissance focuses on gathering intelligence on enemy positions and movements. Targeting involves guiding missiles or other munitions to their targets. And finally, navigation provides crucial navigation and situational awareness for military vehicles and personnel. So, radar jamming is a significant threat to military combat operations, as it can neutralize or degrade radar systems, making it, well, really difficult to detect and track targets. To prevent radar jamming, military forces employ various techniques and technologies. First up, frequency hopping. Radar systems can switch frequencies rapidly, making it difficult for jamming signals to lock onto the radar frequency. And then there's spread spectrum. Radar systems can use spread spectrum techniques, such as frequency hopping or direct sequence spreading, to reduce the effectiveness of jamming signals. Next, we've got pulse compression. Radar systems can use pulse compression techniques, which allow them to transmit long pulses while maintaining high range resolution, making it harder for jamming signals to affect the radar. And finally, phased array radar. Phased array radar systems can steer and shape the radar beam electronically, allowing them to reject jamming signals and focus on the target. So, adaptive filtering, well, radar systems can actually use adaptive filtering techniques, like least mean squares or recursive least squares, to remove jamming signals from the radar signal. And spatial filtering is another approach. Radar systems can use spatial filtering techniques, such as beamforming, to reject jamming signals that are coming from specific directions. Polarization diversity is another tool in the radar toolbox. Here, radar systems can use polarization diversity, which basically means transmitting and receiving radar signals with different polarizations to reduce how effective those jamming signals are. Plus, randomization helps too. Radar systems can randomize their transmission parameters, things like frequency, amplitude, and pulse width, to make it really difficult for jamming signals to predict or counter the radar signal. Redundancy is pretty important as well. Military forces can use redundant radar systems, so there's backup capability in case one system gets jammed. And then there's electronic countermeasures, or ECCM. Military forces can use ECCM techniques like jamming the jammer or even using anti-radiation missiles to try and neutralize the jamming threat. Technologies to prevent radar jamming include, first, Active Electronically Scanned Array, or AESA. ESA radars use a large array of transmit and receive modules, which can be controlled electronically to steer and shape the radar beam. Second, Digital Radio Frequency Memory, or DRFM. DRFM systems can store and replay radar signals, allowing them to mimic the radar signal and, well, confuse the jammer. Third, we have cognitive radar. Cognitive radar systems can adapt to changing environments and adjust their transmission parameters to minimize the impact of jamming signals. Fourth, software-defined radar. Software-defined radar systems can be reconfigured and updated to counter emerging jamming threats. Fifth, advanced materials. Advanced materials such as metamaterials can be used to design radar antennas that are resistant to jamming signals. So when it comes to tactics for preventing radar jamming, there are a couple of key approaches. First, we've got emission control, or EMCON. Military forces can use EMCON protocols to, minimize radar emissions and really reduce the risk of getting detected by jamming systems. Another method is radar silence. This means that military forces can maintain radar silence by turning off their radar systems altogether, which helps them avoid detection by those jamming systems. Next up, there's decoy radar. Military forces can use decoy radar systems to deceive jamming systems and protect their actual radar systems. And then there's jamming detection. Military forces can use jamming detection systems to, detect and locate jamming sources, which allows them to take the right countermeasures. Electronic warfare, or EW, is where military forces can, use EW systems to detect, disrupt, and even neutralize jamming systems. When it comes to training and exercises, radar operators should really be trained to recognize and respond to jamming signals. Military forces can, conduct jamming simulation exercises to test their radar systems and develop countermeasures. And of course, they can also conduct EW exercises to practice detecting and neutralizing jamming systems. By employing these techniques, technologies, and tactics, military forces can reduce the risk of radar jamming and maintain their ability to detect and track targets in combat operations.